A seedling is a young plant sporophyte developing out of a plant embryo from a seed. Seedling development starts with germination of the seed. A typical young seedling consists of three main parts: the radicle, the hypocotyl, and the cotyledons. The two classes of flowering plants are distinguished by the numbers of seed leaves. Monocotyledons have one blade-shaped cotyledon, whereas dicotyledons possess two round cotyledons. Gymnosperms are more varied. For example, vine seedlings have up to 8 cotyledons. The seedlings of some flowering plants have no cotyledons at all. These are said to be cotyledons. The plumule is the part of a seed embryo that develops into the shoot bearing the first true leaves of a plant. In most seeds, for example the sunflower, the plumule is a small conical structure without any leaf structure. Growth of the plumule does not occur until the cotyledons have grown above ground. This is epigeal germination. However, in seeds such as the broad bean, a leaf structure is visible on the plumule in the seed. These seeds develop by the plumule growing up through the soil with the cotyledons remaining below the surface. This is known as hypogeal germination, photomorphogenesis, and etiolation. Dicot seedlings grown in the light develop short hypocotyls and opened cotyledons exposing the epicotyl. This is also referred to as photomorphogenesis. In contrast, seedlings grown in the dark develop long hypocotyls and their cotyledons remain closed around the epicotyl in an apical hook. This is referred to as scotomorphogenesis or etiolation. Etiolated seedlings are yellowish in color as chlorophyll synthesis and chloroplast development depend on light. They will open their cotyledons and turn green when treated with light. In a natural situation, seedling development starts with scotomorphogenesis while the seedling is growing through the soil and attempting to reach the light as fast as possible. During this phase, the cotyledons are tightly closed and form the apical hook to protect the shoot apical meristem from damage while pushing through the soil. In many plants, the seed coat still covers the cotyledons for extra protection. Upon breaking the surface and reaching the light, the seedling's developmental program is switched to photomorphogenesis. The cotyledons open upon contact with light and become green, forming the first photosynthetic organs of the young plant. Until this stage, the seedling lives off the energy reserves stored in the seed. The opening of the cotyledons exposes the shoot apical meristem and a plumule consisting of the first true leaves of the young plant. The seedlings sense light through the light receptors phytochrome and cryptochrome. Mutations in these photoreceptors and the signal transduction components lead to seedling development that is at odds with light conditions. For example, seedlings that show photomorphogenesis when grown in the dark. Seedling growth and maturation. Once the seedling starts to photosynthesize, it is no longer dependent on the seed's energy reserves. The apical meristem start growing and give rise to the root and shoot. The first true leaves expand and can often be distinguished from the round cotyledons through the species-dependent distinct shapes. While the plant is growing and developing additional leaves, the cotyledons eventually senescent fall off. Seedling growth is also affected by mechanical stimulation, such as by wind or other forms of physical contact, through process called thigmomorphogenesis. Temperature and light intensity interact in their effect on seedling growth at low light levels, about 40 lumens per square meter a day. Night temperature regime of 28 degrees Celsius, 13 degrees Celsius is effective. A photoperiod shorter than 14 hours causes growth to stop. whereas a photoperiod extended with low light intensities to 16H or more brings about continuous growth. Little is gained by using more than 16H of low light intensity once seedlings are in the free growth mode. Long photoperiods using high light intensities from 10,000 to 20,000 lumens per square meter increase dry matter production, and increasing the photoperiod from 15 to 24 hours may double dry matter growth. The effects of carbon dioxide enrichment and nitrogen supply on the growth of white spruce and trembling aspen were investigated by Brown and Higginbotham. Seedlings were grown in controlled environments with ambient or enriched atmospheric CO2 and with nutrient solutions with high, medium, and low N content. Seedlings were harvested, weighed, and measured at intervals of less than 100 days, and supply strongly affected biomass accumulation, height, and leaf area of both species. In white spruce only, the root-weight ratio was significantly increased with the low nitrogen regime. CO2 enrichment for 100 days significantly increased the leaf and total biomass of white spruce seedlings in the high-N regime, RWR of seedlings in the medium-N regime, and root biomass of seedlings in the low-N regime. First-year seedlings typically have high mortality rates, drought being the principal cause, with roots having been unable to develop enough to maintain contact with soil sufficiently moist to prevent the development of lethal seedling. Water stress. Somewhat paradoxically, however, eyes observed that on both mineral and litter seedbeds, seedling mortality was greater in moist habitats than in dry habitats. He commented that in dry habitats after the first growing season, surviving seedlings appeared to have a much better chance of continued survival than those in moist or wet habitats, in which frost heave and competition from lesser vegetation became major factors in later years. The annual mortality documented by eyes is instructive. Pests and diseases. Seedlings are particularly vulnerable to attack by pests and diseases and can consequently experience high mortality rates. Pests and diseases which are especially damaging to seedlings include damping off cutworms, slugs and snails. Transplanting. Seedlings are generally transplanted when the first pair of true leaves appear. A shade may be provided if the area is arid or hot. A commercially available vitamin hormone concentrate may be used to avoid transplant shock, which may contain thiamine hydrochloride, naphthalene-acetic acid and indole butyric acid. Images. Bibliography. P.H. Raven, R.F. Evert, S.E.I. Korn, Biology of Plants, 7th edition, W.